Hello, and welcome to the Pre-Med Academy Chemistry course. In this lesson, we will deal with the atom. In the past, the atom was thought to be the smallest particle of matter. It was believed that it could not be broken down into any other subparticles, hence its name. In ancient Greek, the meaning of the word atom is basically indivisible. But over the years and with research, scientists have discovered that the atom can actually be broken down, and even the atom itself is made up of several different subatomic particles. In this lesson, we will learn about these subparticles and how exactly they make up the different parts of the atom. As you can see in the diagram on the right, the atom is made up of two main parts, the nucleus and the orbitals. The nucleus is located at the center of the atom and is very dense and small relative to the total size of the atom. In the nucleus, you can find protons and neutrons. The protons are particles with a positive electric charge, and the neutrons are neutral particles, meaning they have no electric charge. Both protons and neutrons are large particles with more or less the same mass. We say that the mass of protons and neutrons is significant relative to the mass of electrons. Sometimes we say that protons and neutrons are heavy particles in the subatomic scale. What does that mean? It is clear that they are not really heavy, they are subatomic particles. They are tiny. However, in the subatomic scale, they are considered relatively heavy. And again, relative to what? Relative to the electrons, which we will meet soon. Thus the atomic nucleus, although small, contains almost all the mass or weight of the atom. Let's continue to electrons. Electrons are very small particles, which we find in orbitals, which make up the outer part of the atom. The orbitals are also called the electron cloud, because the electrons move through them and form a kind of cloud around the nucleus. The electrons are negatively charged particles, and like we said, they are very, very small, meaning their mass is really negligible relative to the mass of a proton or neutron. How negligible? Almost 2,000 times lighter. In other words, on the subatomic particle scale, they are very small and light. Together, protons, neutrons, and electrons are called subatomic particles. The number of protons in an atom determines the type of the atom, also called the element. We know that there are about 120 different elements in the universe. If you look around you, all the materials you see are made up of one combination or another of these 120 elements. We will deal more with the elements in the next lesson when we learn about the periodic table. For now, just know that different elements differ from each other in the number of protons they have in the nucleus. In other words, the number of protons, and only that number, determines the type of element an atom is. Let's look at some examples. All the atoms of hydrogen, which is the lightest, smallest element, have one proton. And if we find, somewhere in the universe, an atom that has one proton, we will know for sure that it is a hydrogen atom. Another example, all the carbon atoms have 6 protons, no more and no less. And a final example, all iodine atoms in the universe have 53 protons. Now let's talk about two important terms. The first term is atomic number, and the second term is nuclear charge. In the end, they both actually tell us how many protons there are in the atomic nucleus. But let's understand why. An atomic number basically tells us the type of atom, or in other words, what the element type is. Each element has a unique serial number, from 1, which represents the element hydrogen, the lightest and smallest atom, to about 118. And what did we just say that differentiates different elements? The number of protons. It therefore makes sense that the atomic number that defines the atomic type should be determined by the number of protons. As for the nuclear charge, if we recall again what the nucleus is made of, it is made up of protons and neutrons. Remember, neutrons are neutral, they have no electrical charge. In contrast, protons have a positive electric charge. The electric charge of the nucleus is the sum of the charges of all the particles that make up the nucleus, the protons and the neutrons. But because neutrons have no electric charge, the nuclear electric charge ends up being the sum of the charges of the protons only. And if each proton has a charge of +1, then the total charge of the nucleus is simply the number of protons. Therefore, the number of protons is also the nuclear charge. Let's define another term, mass number. The mass number is a number that represents the mass or weight of an atom and is equal to the combined number of protons and neutrons that are present in the atom. Let us understand why this definition represents the mass of the atom. We said that protons and neutrons are the heaviest particles in an atom and that their masses are very similar to each other. In contrast, electrons are very small and their mass is negligible. Therefore, if we want to indicate the overall atomic mass, there is no need to count the electrons, they are insignificant. Therefore, we will count only protons and neutrons. This is basically the logic behind the definition of mass number, counting the number of protons plus the number of neutrons. In the previous slide, we talked about different elements. What distinguishes one element from another? We said that one element has a certain number of protons, and another element will have a different number of protons. We will describe a phenomenon in nature, in which a particular element appears in a number of different types, each type having a different number of neutrons. To explain this, it is most convenient to use examples. Look at the example on the left. It says isotopes of hydrogen. Ignore for a moment the word isotopes, we will explain it in a minute. What can we see in the example? First of all, we see 3 atoms of hydrogen. How do we know that these are hydrogen atoms? Because the nucleus of each atom has 1 proton, and we said that all the atoms in the universe that have 1 proton are hydrogen atoms. Here is a single proton, marked here as a circle with a small plus. So what differentiates these atoms from each other? The number of neutrons in the nucleus. The left atom has no neutrons at all, and that may seem a little strange to you, but it's just fine, such atoms do exist. The truth is that most hydrogen in the universe is of this type, having no neutrons at all. There doesn't have to be neutrons in the nucleus. The middle atom has 1 neutron in its nucleus, in addition to the proton, here it is, and the right atom has 2 neutrons in its nucleus, in addition to the single proton, here they are. So we have 3 atoms of hydrogen, but they differ from each other in the number of neutrons they have in their nuclei. Let's look at another example, isotopes of nitrogen. Again, we will define the term isotope shortly. For now, let's look at the example. If we look at the periodic table, which we will delve into in the next lesson, we can see that all the nitrogen atoms in the universe have 7 protons. And indeed, all 3 atoms in the example have 7 protons in the nucleus, so we know that these are indeed nitrogen atoms. But they are not the same. What differentiates them? The number of neutrons they have is not the same. In the left atom, we have 7 neutrons. In the central atom, we have 8 neutrons, and in the right atom, we have 9 neutrons. How do we name these 3 different atoms? The left atom is called nitrogen 14. Do you see? Here. Why? Simply add the 7 protons to the 7 neutrons and get 14, which is the mass number of the left atom. The middle one is called nitrogen 15. Why is that? Because 7 protons plus 8 neutrons come out 15, meaning its mass number is 15. And similarly, the right atom is called nitrogen 16 because 7 protons plus 9 neutrons give a mass number of 16. So, what is this strange phenomenon? We can see that in nature, there exist atoms of the same element that differ in the number of neutrons they have. This phenomenon is called isotopes. These 3 are isotopes of hydrogen, and these 3 are isotopes of nitrogen. So let's finally define isotopes as atoms of the same element, having the same atomic number, but a different mass number. Why is their atomic number the same? Because they are the same element, they have the same number of protons. And why a different mass number? Because they have a different number of neutrons, and the mass number consists of the total number of protons and neutrons in the nucleus. Now let's move on to electrons. Let me remind you that electrons are found in orbitals, not in the nucleus. They move around in the space around the nucleus, also known as the electron cloud. When the number of electrons is equal to the number of protons, we say that the atom is electrically neutral, or simply neutral. This should not surprise you, because as we've explained, electrons are particles with a negative electric charge, and protons have a positive electric charge. So if the amount of positive charge in the atom is equal to the amount of negative charge in the atom, then the whole atom is neutral. What we will see later, in a few lessons, is that different elements tend to gain or lose electrons and become something we call ions. An ion is actually an atom whose total charge is not neutral, but is positive or negative. And how can this happen? Because for some reason, the number of electrons is not equal to the number of protons. We have 2 types of ions, anions and cations. An anion is a negative ion, and it is formed when the number of electrons becomes greater than the number of protons. This means that the atom has received additional electrons, at least one more electron. An atom may receive more than one electron, and we will explain how and when this happens in following lessons. On the other hand, we have the cation, which is a positive ion. It is formed when the number of electrons is less than the number of protons, which means that the atom has given off electrons, at least one. Why gave off? Because, if the atom gave an electron, it means that it gave away a negative charge, because electrons are negative. That is, the atom now has more positive charge than negative charge, so the whole atom becomes positive. Notice a critically important point. Ions are never formed by a proton leaving or joining the nucleus. It is always a matter of electrons leaving or joining orbitals. Why is that? Because if a proton leaves or joins a nucleus, we actually get a new element. After all, we said that the number of protons in the nucleus defines the element. So if suddenly the number of protons changes, we actually have a change in the element type, and this is another phenomenon called radioactivity, which we will not discuss now. Each element, and recall, there are about 120 elements, has a unique chemical symbol, agreed upon by all chemists. The chemical symbol is a capital letter in English, or for some elements, is a combination of a capital letter and a lowercase letter. The letters were chosen based on the element name in English or in other languages. Let us look at some examples. For instance, the chemical symbol for carbon is a capital C, derived from the English word carbon, which begins with the letter C. For sodium, we have a chemical symbol of a capital N and a lowercase a. Obviously, this chemical symbol came from some language other than English. Magnesium has a chemical symbol of a capital M and a lowercase g, and chlorine has a chemical symbol of a capital C and a lowercase l. In addition, there is an official way in which we can describe the atomic number, the mass number, and the charge of a particular atom. The atomic number is written on the bottom left-hand side, the mass number is written on the upper left-hand side, and the atomic charge is written on the top right-hand side. And yes, it is very important to follow the positions of these different numbers relative to the chemical symbol itself. Let's take a look at some examples of formal chemical symbols. In the first example, you see the element carbon. Carbon is denoted by the capital letter C. Below on the left, you see the number 6. This is the atomic number, meaning how many protons there are in carbon. In addition, the top left side has the mass number, and here, in this specific carbon atom, it says 12. From these two numbers, 12 and 6, we can always understand how many neutrons are found in the nucleus, because if the mass number describes how many protons and neutrons in total the atom has, it is possible to do 12 minus 6 and get that there are 6 neutrons in the atom. Note that nothing is listed on the top right. We just said that on the top right, you can list the charge of the atom. But if nothing is written, it means that this atom is neutral, because we never write a zero charge. In a neutral atom, the number of electrons is equal to the number of protons. Therefore, we can conclude that the number of electrons in this carbon atom is also 6. Another example, here is a chlorine atom, which we mark with a capital C and a lowercase l. Chlorine is atom number 17 in the periodic table, meaning it has 17 protons. The mass number of this specific chlorine atom is 35, which means that the total number of neutrons plus protons is 35. Of course, we can calculate the number of neutrons if we do 35 minus 17 to get 18. This is the number of neutrons. And now a confusing part. On the top right, we see the number -1. This means that the charge of this atom is -1. -1 means that this specific chlorine atom is a negative ion, what we called an anion. This tells us that an extra electron has been added to a neutral chlorine atom. Why is that? Because electrons are negative particles, and if we add another electron, the charge of the whole atom will become more negative. Therefore, instead of the 17 electrons we would expect to find in a neutral chlorine atom, same as the number of protons in chlorine, here we have 18 electrons, that is, one more electron. Why is this confusing? Because a lot of students look at that -1 and actually think it means -1 electron, which means that the atom lost one electron. But do not get confused, the -1 here is not how many electrons were added to or dropped from the atom, but what the total charge of that specific atom is. And if the charge is -1, it means that an electron was actually added to the atom, because electrons are negative particles. And now for our last example. We see a magnesium atom, a capital M and a lowercase g, with an atomic number of 12, meaning it has 12 protons. The mass number of this specific magnesium atom is 24. By the way, there may be other magnesium atoms in the universe, isotopes of magnesium, whose mass number is different. But in this magnesium atom, the mass number is 24. From this, it is possible to deduce the number of neutrons, 24 minus 12, that is, 12 neutrons. And finally, and this part is again a bit tricky, the charge is +2, which means it's a positive ion. We called it a cation. It has a +2 charge. This means that this specific atom of magnesium actually lost 2 electrons. Why did it lose 2 electrons? Because electrons are negative, and if the atom has lost a negative charge, then the whole atom becomes more positive. So note, if the atom were neutral, then the number of electrons would be equal to the number of protons, which is 12. But because it has a +2 charge, it means it has lost 2 electrons, and it only has 10 electrons. And lastly, a very important note. From time to time, you will see that the atomic number is not written at all on the bottom left, which is actually not so strange, because the atomic number is in fact unnecessary information. Why is that? Because you will always have a copy of the periodic table with you, and if you are given the chemical symbol of the element, that is, given the letter or 2 letters in English that represent it, then you can always go to the periodic table, look for the element, and see what its atomic number is. Therefore, it is not mandatory to write down the atomic number on the bottom left, and you will see that quite often. For example, here is again the magnesium atom from the previous example, but this time, we did not mark the atomic number. And it's very easy to go to the periodic table and just find that the atomic number of magnesium is 12. That is, it has 12 protons. Note that we must still write down the mass number of this magnesium atom and its charge, because we are not given mass numbers or atomic charges in the periodic table. Why is that? Because most atoms have a number of different isotopes with different mass numbers. And each atom can have different types of ions with different total charges. So the mass number and the atomic charge still have to be written down.